Is everyone back in the room? So, great. I've derived some speculative form of formulae that were derived more rigorously. And the only reason that I want to use them in this form is because they will work. And they correspond to these under some assumptions, which will be true since they work. If they didn't work, probably some of the steps were not justified enough, at least even at the lowest order. Great. So something else that I need to introduce to apply on-shell methods for the picture that we're having is I basically want to set this particle on shell to be able to use even this picture. So the way I drew this picture was like we have two amplitudes and there's a cut, because otherwise I wouldn't be drawing blobs there in the first place. And it doesn't exactly correspond to what those formulas say, because those formulas say that my momentum should go to 0 as a whole. It expects the momentum to be real, space-like actually. So yeah, by the way, k squared is just p1 minus p2 squared. You can see that it's smaller than 0. Say in the rest frame, you can write it as this minus p1, p2. And p1, p2 is over m squared. p1 m squared, p2 m squared, and plus p1, p2 as 3 vectors, m squared. And in the frame where they are more or less equal, since k is small, you see that it should be smaller than 0. So it is space-like. So it becomes p squared. And these two guys win over that guy. So, oh wait, they don't win. There's this 1/2. You would go to the next level, and then it would probably win. Yeah, okay. Yeah, there is a more exact way to show that it's 0, that it's smaller than 0. But the point is that it's space-like if it's real. And I want to, but then it goes to 0 as well as k becomes smaller, as rescaled by h bar. But at the same time, we're looking at the spinning case, so we want to get multiples out. So a multiple of some degree L will behave as some power of k as a 3 vector, which is non-zero, and some spin vector. So if we just let it go to 0, there's danger that we will actually lose the loop dependence and the spin dependence. And we saw that for Kerr black holes, they are packaged into nice exponentials that also, where is it? No, here, exponentials that contain that rule. So it's nice to actually not have it go to 0 as a whole, but rather set it first complex and light-like, and do everything as if that was true. So that will never kill any terms like that. So we will preserve our spin dependence. And only at the very end, we analytically continue to real small space-like transfer momenta. And this is called, null. This is called holomorphic classical limit. And Alfredo introduced it in 2017 in his solo paper. Great. So this is the justification for using on-shell. This on-shell diagram now. And so let me compute it. So I'm computing this four-point function, and its residue comes from two helicities, two graviton helicities exchanged up to other corrections. So where t is of course k squared. So I'm still considering it. I'm considering it going to 0 first, and on the pole, I'm allowed to use my amplitudes. P1 minus P2 kh, P3 minus P4 k minus h. So now I can just plug in my amplitudes. I will need to distinguish between masses if I want to be doing the general case. 2sa minus 2, no, minus 1. No, minus 2 is its gravity. 2sb minus 2, t from the propagator, and then something very simple. So let me first write it in the fully chiral basis. So this came from the helicity plus. Let me do the helicity minus as well. The helicity of k, and so minus k has the opposite. I'm still doing everything in the chiral basis. Well, I've done something quite arbitrary. Clearly, if I use this basis, this would be collapsed into something that doesn't have any apparent dependence on spin, whereas this would be blown up into some spin dependence. So at the moment, it seems like if whatever I've done contains some spin exponentials, but it contains something quite, it is a chirality dependent statement so far. So it's true, but it doesn't help me to read off anything sensible on the classical part. And to read something, something sensible in the classical part, I want to do the following. I want to remember that actually P1 and P2 are slightly different. So P2 as a momentum can be obtained from P1 as a momentum. We use tau and sigma here. And of course, they can be Lorentz transformed into each other because they have the same mass. So they live on the same mass shell. You can just boost one to the other with this Lorentz transformation. So this will be sigma mu nu, which is the vector representation generator. To have such a simple this is tau. Yeah. To have such a simple formula for this boost, you need k to be massless. The formula would be more complicated in the off-shell case. Well, once you have something like that, you can also realize that that a spinner, a massive spinner for vector 2 with index b, can be obtained from massive spinner for momentum 1 by doing a similar boost. Well, since it's a spinner, I have to use, so yeah, I forgot to contract tau and sigma here. Since it's a spinner, I have to use sigma mu nu spinner generators, 2x2 spinner generators. And OK, this converts me to something with momentum corresponding to momentum 2. But of course, there's a redundancy, there's a little group redundancy in how I define this in the first place. I don't have to define this in a way that respects how I define it for the other momentum. So in principle, there must be some unitary SU2 transformation between indices for momentum 1 and indices for momentum 2. And similarly, for this guy, I'm allowed to write that, which is just, again, the boost in the in the right-handed representation. And since the same momenta is here, the residual gauge, the residual little group transformation will have to be the same. So for the spinners that I actually have, I'll write it in this form. Now let me forget about this. 1, 2, 1. Now we have different spins, A on one side, and something else we can do here. Sigma mu nus are self-dual and anti-self-dual in the chiral and anti-chiral representation. So this holds, and this holds. And just like before, OK, whatever. Here it's consistent. Bar. So these properties are just numerical properties of the chiral and anti-chiral Lorentz generators. And since I'm allowed to put some Levi-Civita inside of here, I can then rewrite the same exponents in terms of a polar Lubansky vector. So this is nice. The Polylomansky vector will be now on this side, it will look like that. Just E minus Ka of A. And I will also use it for 4. We also have for 4 here. Now it's another little group transformation. So 3 and 4, of course, have the same mass, so they can boost it in the same way. And the only difference here is that my momentum K goes the other direction, so I put a plus here. And the spin operators are understood in the tensor product sense, of course, as constructed out of 2x2 Lorentz generators. And it turns out that once I take that into account, which is well motivated by the classical picture in which spins should be defined with respect to some frame, and since I want to read off something classically sensible, I want these frames to be the difference in frames with respect between state 1 and state 2, I want it to be accounted for in some way. And it turns out that, at least in this way, I gain some dependence for myself, some spin dependence that will be crucial for me. So now I can rewrite these. Well, I can just do it here now. No, I won't be doing it here. Let me maybe even use another board for that. Yeah. So the whole value of M4 is equal to minus I kappa over 2 squared and masses. Well, the T transfer momentum squared. Still the Helicity factors. I haven't done anything with them yet. And so there, I will cook myself a spin dependence of the form Ka with a minus, yes, with a minus uh, 3, 4. So factor of 2 there will cancel because of an additional factor, exponential factor. And here it will be the opposite. The factor of 2 cancels here. This is A. B. B. Now, consider something that that definitely shouldn't be interpreted as having spin dependence. For general spin, it is equal to this times that. And this we can open up and actually it will indeed have spin exponentials with opposite signs. S. Moreover, yes, so this, the way I wrote this in the angle spinor brackets, it can be checked now that it doesn't depend on the choice. I could have written it in this way, and it would still be the same exponents. They would act differently because they would correspond to right-handed generators as opposed to left-handed generators, but this is still true. So now I have some spin dependence in my quantum amplitude in terms of operators that doesn't depend on the choice of my basis. And on top of that, if I, so I want to do something with the quantum pieces that live here that look like states. This is going to be an heuristic thing, but I'm going to call it M4K in some brackets. But this will be the classical expression corresponding to this quantum expression that has been so far written exactly. K squared. And I claim that so whenever there's 1A, 1B for some momenta, remember that that's just a factor of mass times Levi-Civita. So this is a unit operator, especially if we lower indices up to a minus sign, which I don't track anymore. So if I now consider this exponent as being outside of its operation as a classical spin dependence, then 1 and 1 collapse with each other. And I just get a bunch of masses and unity operators. So in the end, by doing this heuristic operation, I would get something like just U12 to the 2s. So, and this is unitary. And if I do the same thing here, if I pull out the spin dependence out of this operator dependence, then this would collapse, give me some masses that would kill off these guys. So actually, I should not be writing that here anymore. And also, there would be leftover unitary transformation matrices But they belong to some kind of normalization that comes just from the states, from the polarization vector states, tensors, polarization tensors. So I can just consider all of that as leftovers of the quantum picture, and they're unitary, so I consider them to be equal to be equal to 1. So I'm just going to write something like that. Moreover, well, so there are these helicity factors, and one can show that they're equal to gamma 1 plus v squared and gamma 1 minus v squared, where gamma and v, well, gamma is related to v through the standard notation in special relativity, and they're defined to be 2pa dot pb over, no, without the 2, ma mb. So this is just the Lorentz product of the four velocities of two incoming black holes. And so this is going to be my expression that I can use. So this is the most heuristic part of what's been happening, and it's going to become much more rigorous after we write a paper with Donald, hopefully soon. Great. And since I'm running out of time, my next step I will not go into any details with respect to the next step. Wait a second. Oh, yeah, by the way, here, when I wrote that in momentum space, of course it was wrong. I meant the formula that I started with contained a Fourier transform, two-dimensional Fourier transform. So if I define MB in position space, where B is the impact parameter for my classical scattering, if I define it to be, well, that measure, it was G4K delta PAK delta PBK and 4K. And using the fact that B as an impact parameter, it must be transverse to the incoming momenta in the classical picture, I can just perform this Fourier transform. It's a two-dimensional Fourier transform. It's easiest done in the center of mass frame, but the answer can be written absolutely Lorentz invariantly if I find the right sheet. So just by performing this transform, I get this expression. Oh, wait. What is it? Okay. I also trade kappa squared for my Newton constant, and I get it in something sensible. Yes, there are extra factors of gamma and V that give me that. So there's still a sum over two helicities, and and then there's an exponent. And this exponent, there's a final rewriting that I must do before I'm allowed to do this Fourier transform. This Fourier transform is already an absolutely real transform. So for that, I need to consider K to be space-like and real. But here, I was still writing something chiral, and classically, it doesn't make any sense. So to have a chiral exponent in, well, in any expression whatsoever. So that exponent, so there's the sum over plus minus plus minus Ka. I can, there's on shell, on the complex kinematics, I can rewrite it in a gauge, in a parity even way. And it becomes that. And then when I take the Fourier transform, the exponents combined with the exponent in the Fourier transform, and all of it ends up being this interesting combination, written absolutely Lorentz invariantly. And then we can just plug it into this formula and observe that the result compares exactly with Justin's calculation using classical linearized gravity. So this is a calculation, a classical calculation that he did himself 3 years ago, and it gives you absolutely, for general spins, it gives you the linear order impulse and angular impulse. And we get them, we obtain them just by using the 3-point vertices that I've spent so much time talking about for general spin. So they contain all of the information that's needed to get these results that I didn't write, but you can just shove that in, take derivatives, and this is precisely his expression in his paper way back. Oh, no, not way back, actually, just 3 years ago. So it's even classically, if that's any measure, it has only been done a couple of years ago. So, this is the end of it. This is the end of the lecture. If I've been showing you 4-point and even higher point amplitudes at tree level, but I ended up using only 3 points. So that may be underwhelming, but let me tell you that in a one-loop calculation, so it's g Newton squared, you would have to consider the main, the crucial contribution comes from this diagram. 1, 2, 3, 4. And here you really need the Compton amplitude that we've been also working on. And some new results have been produced using that at the next order. As opposed to this, what I've been showing here is a rederivation of a known result, although just obtained a couple of years ago. But at one loop, for aligned spins, we could get some new results. They are conjectural because the whole thing is quite heuristic. So we were basically in the published version, you can see that all of this is conjectural, which is absolutely correct. But they are consistent at linear order with results by Bini and Damour for aligned spins, and consistent with some conjectural, but from the classical point of view, conjectural results at quadratic ordering spin at 2 p.m. So yeah, this is just, without any derivation, just to tell you that you can go higher than that. Well, thanks a lot for your attention. Yes?
So what are the steps that you need to go from this to predicting a Lagrange waveform?
I haven't been thinking that hard about that, just hoping that my more classically oriented collaborators would think about that on my behalf. There are non-trivial steps, a lot of work there as well. Consistency checks.
For example, if I were to compute the usual amplitude, I would then check if it matches in the collinear or soft limit.
Right. Yes, there are. So yeah, you can use the test body limit, where one of the masses is small, and then it's a much simpler problem because that's just a test particle in a known space-time. And Justin has checked those limits more recently. Actually, he has written a paper in September, I think, where he has he has reproduced a very similar formula from the classical point of view to the one loop formula that I don't have on the board, but yeah, something very similar comes out of the test particle limit classically. So that's one nice check.
So for this analysis, we use like a space, a flat space, right? Like
Yes.
Say eta mu plus h mu. Could you generalize on this for like a pure background?
No, it's well, in principle, yes, but really no, because we use we use the on-shell approach in flat space. So there is work on using amplitude-like ideas using the double copy on non-perturbative backgrounds, but I think they involve shock waves, so they don't look like I don't think they look like a nice black hole source. And the way we use our covariance on the amplitude side is all flat space spin covariance, helicity counts. All of those notions are rooted in QFT in the flat space. Yeah, I wouldn't know what exactly to do.
Sort of sociological question. Did you get interest from like gravity people?
Yes. They are quite positive. They are optimistic and supportive. Well, at least some of them. Well, there are higher high PN results available from classical calculations using different classical methods. Those are post-Newtonian results that are hard to compete yet, even in the spinless case, but the new PM results by the Californian group, they contain all orders and velocities which are omitted in the post-Newtonian approach. Well, they are gradually included with each order in the post-Newtonian expansion, but once you do a post-Minkowskian expansion, the way I phrase everything here, you have all orders in velocity at this order, at the specified order in the coupling constant. So yeah, there's definitely new results coming on that side, and if you count orders in V, that's an infinite number of new results. What I've been concentrating on here was the spin dependence, and the spin dependence is complicated in the classical theory, very much so, and that's why we're doing it, because even the tree level general solution was only done a couple of years ago. So it's absolutely, it was very surprising to me that you can do something new at one loop, and the classical people, for them it's new. It's good that they also have results with which we can check, like this linear in spin thing. That was derived by Bini and Damour in 2017 as well, at second post-Minkowskian and linear in spin. They derived it, and our conjectural result that I don't have on the board, but that uses this cut, it reproduces that result and contains much more information, which hopefully makes some sense.
Good. So,
Thanks.
I think we should really thank one more time Alexander for this very interesting interdisciplinary lectures.
Thanks.
Before you run away, wait for 1 second. Could you please come to yeah, so basically we will also
I should be done.
this was a very good moment.